Thank you for the introduction. My talk today will be about time fluid field-based coordination. I'd like to start with a very general discussion about what is time and does time even exist? Why do I ask these questions? Basically, time has been a matter of discussion among philosophers and physics for millennia. And there's a relativistic view of an immutable line of time that goes on, and it's immutable everywhere. And this is fine for many practical applications, but not for all of them. Just to make a simple example, for instance, satellites, GPS satellites won't work under this assumption of time. More recently, modern views are given a different definition of time. It's not settled, the question. And in particular, there are two very diverse approaches to defining what time even is. There are a couple of books in this slide that I recommend. The position that I like most is the one from Rovellis, and it's the relational interpretation of time. Under this interpretation, quantum systems are observer dependent. What does it mean? It means that time has only meaning in presence of events, and basically times depends from a deeper concept, which is causality. Think about the end of the universe. Well, not a very pleasant thought, but it will end in thermal death. And when the universe will have reached this state, there will be no events. With no events, there will be no meaningful way of measuring time. Let's get back to our world and talk about field-based coordination. Field-based coordination is a way of coordinating a distributed system inspired by physics by manipulation of distributed data structures. There are several examples of frameworks that are field-based. I reported 3 here, but there are more. TOTA from Mamei and Zambonelli, fixed point-based computational fields from Lafuente, Loretti, Montanari, and others, and aggregate computing from myself, Zig Beal, Mirko Viroli, Roberto Casadei, and others. Time in field-based coordination is dealt with by mostly abstracting away from it. The designer is meant to focus on the eventual behavior of its software, and usually computation happens in rounds, which means basically sometimes some device wakes up and computes the value of the fields in its own position. Scheduling of rounds is usually dealt with by the platform, so externally from the core field-based computation system. Such scheduling changes depending on the implementations and can be purely reactive, as for instance in TOTA, or can be purely proactive, as it is usually the case in aggregate computing. And finally, it could also be just completely abstracted away with the whole focus on the eventual behavior, like it is in fixed point-based computational fields. Historically, in fact, field-based coordination focuses on space rather than time. Time is usually abstracted away whenever possible. However, in practice, time and space are deeply intertwined. The propagation speed of the events generated by the field computations influences the evolution of the computation itself. Moreover, these kind of coordination systems are usually deployed when there are highly dynamic situations. In such highly dynamic situations, there is often no such a thing as eventual state. The system is in a continuous, eternal, dynamic status where things change continuously, and as a consequence, the system is always in a transient state. So why are we discussing about time and field-based coordination? Well, first of all, we want to have fine-grained control on the dynamics of the system when it is transiting. Second, there are 2 important aspects that need to be considered, which are reactivity, namely how reactively the system can respond to a change in the conditions, and efficiency, namely how many resources do I need to have the system cope with the changes. For instance, think about a landslide monitoring system deployed on the side of a mountain. If there is higher humidity or maybe even beginning of a landslide, then you probably want to raise the rate at which you are evaluating your readings from the sensors. If you're in a situation in which you have no control on the time dynamics of the system, maybe your device is computed at, I don't know, 1 round at hour, it might be more than enough and actually draining your battery when the situation is stable, but on the other hand, being completely insufficient when the landslide is about to happen. What we want to do is to have the possibility of telling the system to behave according to causality. So if there is some reason to accelerate, then accelerate. If there is no reason to compute too fast, then slow down and save resources. There are a number of requirements for this work to be actually useful, and are: first, we do not want to lower the abstraction level. Second, of course, we want to support all the coordination mechanisms that are already in place in field-based coordination. And third, we want to have both the possibility of expressing proactive and reactive behaviors. Our idea is to leverage field-based coordination itself to support the coordination of field programs. We call this approach time-fluid field-based coordination. And the idea is that we create a causality field driving the application level dynamics. How do we do it? So first, we have a number of events that can cause computations. This set of events includes timers and the results of field computations. We associate to every field program a guard policy. The guard policy, when evaluated, produces two things. First, a Boolean, and second, a set of events. How do they work? The Boolean value is meant to decide whether the associated program has to be executed immediately, while the causality field is the set of events that will cause a re-evaluation of the policy and hence possibly a re-execution of the associated application program. Additionally, at Bootstrap, of course, all policy need to be evaluated once. So basically our solution is to associate a guard policy to every field program. Field programs compute by having access to the context of the application, for instance, sensor readings, and to the messages received from the neighbors. The policy computation shares the same domain, and this has a great impact on the expressivity of the system. We like to say that having direct control over the causality field allows to shifting from programming the space in time to programming the space-time. This in turn allows us to be reactive to causality itself, namely speeding up and slowing down parts of the distributed system dynamically depending on the context and on the situation ongoing. Finally, having access to both the current context and received messages allows computation to have great expressiveness, and with great expressiveness comes great responsibility, in the sense that policies, if not well programmed, can easily be intertwined one to each other and cause phenomena like deadlocks and live locks. We reified these ideas into a prototype based on an existing aggregate programming language, which is Protolis. We made no change to the language syntax, so we just reused it as it is, and instead we just implemented the time fluid components externally as platform support. The implementation is available, is online, it's linked in the slides and in the paper, and we use the language itself for writing the policies. So basically, every aggregate computation written in Protolis has a Protolis program associated, which is its guard. This is a code example. It's not really meant to be completely understood. It's just to give you the idea of how it feels. So the biggest difference is the first line is the import. Namely, now the platform must have a way to show events to the developer. The central part of the code shows you that it's a real field computation, even though it's executed inside a policy. In fact, it uses coordination and messages with other devices to establish if the count of people has changed from the last executed round. In the last part, you can see what the computation returns. it's a list of two elements. The first one is a Boolean, deciding whether or not the actual computation should take place. And the second one is the list of events that we want to register to be executed again in case of changes. We evaluated the approach as follows. Basically, we created a network of devices similar to this one. It's an irregular grid, and the scope of each single device is to compute the distance from a source. Sources are marked in red and are the bottom left red node and the one on top. While the bottom one is static as the rest of the network, the top one is mobile and moves from left to right, and then as soon as it exits the scenario, a new one is generated on the left and makes the same path. So what we have here, we have a system that is unbalanced in the sense of what's going on. All the southern western part of the network can stabilize once for all, in the sense that devices do not move and they compute the distance from their source, and they do not need to recompute it again and again and again as it would happen in normal algorithm computing. On the other hand, however, we cannot just lower the rhythm at which the whole system is running. Why? Because there is a node on the top of the scenario which is mobile, and the distance from it needs to get continuously recomputed. We run the experiment by varying both the maximum frequency at which we allow devices to run and the speed of the mobile node. We measure error in terms of how much our distance estimate is wrong with respect to an oracle, and how many rounds are we computing across the network. Why do we count how many rounds? Basically, it's a proxy metric for both communication and energy consumption. So what happens in the system? This is a heat map showing the number of rounds the system is executing. This is a snapshot. It's a sequence of snapshots from the simulation. So when we begin, every device is at 0. With the simulation going on, they will turn redder and redder in the points in which they are computing the most. As you can see, there's an area of the system that basically almost never computes. It's completely yellow. And there's another area on top, and especially on the right hand side, which is instead computing the distance continuously. What's happening in that area and why there's a gradient? Basically, this is due to the particular algorithm we used to compute distances. We didn't use the very best of the available algorithms in literature. We picked one of the simplest, which is a known issue. It's known as the raising value problem. There's a publication about it if you're interested. But basically, it's much more reactive at adjusting the value when the source is getting closer, and much worse when it's getting farther. So what happens here is that the source enters from the left, so the left-hand side has an easier time computing their correct value with respect to the right-hand side when where the source exits the scenario. In the next slides, we can see how the system behaves with respect to the speed of the moving node in terms of numbers of rounds executed and error. Number of rounds will be on the left, and the lower the better, and error will be on the right, and again, the lower the better. So when even the mobile device is static, what we see is that all the implementations have basically 0 error, but still we can see the advantage of the time fluid version. Why? Because it executes way less rounds, so it saves you a lot of energy and bandwidth. When the node starts moving instead, we can see that the situation is that there are configurations for which there is both lower error and lower energy cost at the same time. Of course, if you pick a very, very reactive configuration, what you see is that you consume a bit more energy, but you have a much lower error. See the yellow line. On the other hand, if you run much more slowly, you consume a lot less resources, but you have a bit higher error. There are a lot of configurations in which you can achieve both lower resource consumption and lower error. This is confirmed by tests with higher speed. The peak you can see on the right is due to the fact that the node has run enough to exit the scenario, causing an interruption, and another one is entering, so there's a disruption of a system which was stabilizing. And this is even confirmed by doubling the speed. This case, of course, 2 peaks, because the mobile node has the time to do its path twice. So, concluding, we showed an approach for enriching the existing field-based computation systems with a causality field. The causality field allows to program the space-time rather than the space in time, as it's usually done in field coordination systems. Our proposal doesn't change anything of the host language. It actually just leverages it and its expressiveness to create a causality field. In principle, it's applicable to any field-based coordination language, and we developed a prototype on the aggregate computing framework using the Protelis programming language. In future, our expectation is to evolve the prototype to the point that it can be used on real-world applications, and we're also interested in measuring the exact impact we have on real-world system, at least via realistic network simulation. Currently, as you have seen in the evaluation, we just use the round count as a proxy metric. But we believe that there are a lot of subtle effects due to the shared means of communication that could be improved by this kind of approach. Also, another plan is to bring the approach to other languages, for instance, CAFI, a Scala version of the aggregate computing systems, and if possible, others. So that's it, and I'm very happy to answer your questions if you have any.